Welcome, curious minds, to another deep dive. We're here to take complex ideas and, well, make them crystal clear. Today, we're getting into something really foundational in calculus, the hyperreal numbers. If you're just starting your calculus journey, get ready for maybe some aha moments. We want these concepts to feel intuitive, not, intimidating. We're pulling our insights from Calculus Unbound by Dr. Dustin Potter. It's a great resource. Really helps demystify this stuff.
Precisely. Yeah, our mission today is really to explore how mathematicians handle the unimaginably small and the fantastically large. And crucially, why understanding these numbers is kind of a secret to unlocking the power of calculus. Think of this deep dive as maybe your shortcut to understanding the why behind those tricky early calculus concepts, giving you a concrete way to approach ideas that might have seemed abstract before.
Oh, let's try and unpack this. When we talk about infinitely small or infinitely large numbers, I mean, this sounds almost philosophical, right? Not really mathematical. Why do we even need numbers like these in calculus? What problem are they actually trying to solve?
That's a really excellent question, and it goes right to the heart of how calculus even started. You have to imagine Isaac Newton and Gottfried Leibniz, the founders of calculus. They were grappling with these fundamental questions about motion, about change, like how fast is something moving at one exact instant? Or how do you calculate the precise area under a curve that's constantly changing? To answer these, they sort of instinctively felt they needed to break things down into like tiny nudges or zoom way out to huge scales. But the numbers they had, the real numbers we all know, they didn't quite have the tools to properly formalize these tiny nudges or huge scales. Not directly, anyway.
Okay, so if I'm getting this right, it's like we needed both a super-powered microscope maybe to see the tiniest details and also a kind of cosmic telescope to grasp the biggest perspectives.
Yeah.
And without both, you're missing the full picture of, well, in this case, change in motion.
That's a perfect analogy, yeah. The real numbers, they're great for everyday stuff, measurements and things, but they just aren't quite enough to capture those extreme perspectives, and that's exactly why we need the hyperreal numbers. They basically equip our mathematical toolkit with both that superpowered microscope and that cosmic telescope.
Okay.
And what's really, I think, profound here is that this approach lets us define concepts like the slope of a curve or the instantaneous velocity of an object directly. It feels incredibly intuitive this way. For example, Dr. Potter's work shows how defining the slope of a curve, say y equals x squared, right at a single point, well, it requires us to think about small enough changes in x and y.
Right, the tiny nudges again.
Exactly. The hyperreals give us actual mathematical objects for those small enough changes. Instead of only relying on the, let's say, indirect idea of limits, it makes the instantaneous feel more tangible.
That definitely makes the why much clearer. So these hyperreal numbers, they really expand our number line. They add new dimensions to it. What are the key categories then, the players in this new expanded universe of numbers?
Yeah, Dr. Potter's Calculus Unbound categorizes them really nicely into three main types, and it truly extends how we think about the number line. Okay, so first, we have infinitesimal numbers.
Infinitesimal.
These are numbers that are, well, they're unimaginably tiny, just incredibly small. Think smaller than a speck of dust, smaller than an atom, but still, crucially, greater than zero. The book describes an infinitesimal as like the tiniest grain of sand your mathematical microscope can possibly detect.
Wow.
And what's fascinating is if you take an infinitesimal and add it to a regular real number, it creates a value that is infinitesimally close to that real number. This concept is so central, the source actually calls it a halo.
A halo, like an aura.
Precisely, yeah, an invisible aura. Imagine a real number, like a bright point on the number line. Its halo is this tiny, invisible cloud, maybe?
Yeah.
Of all the hyperreal numbers that are just a microscopic distance away from it, it gives us the mathematical precision to talk about arbitrarily close in a very direct, very concrete way.
So infinitesimals are like the superfine dust, the quantum particles of the number universe, allowing us to zoom in, like infinitely close. Okay, what's next in this expanded system?
Then you have the appreciable numbers. These are basically the normal size numbers we already use every day. Essentially all the familiar real numbers, -10, 0, 5.2, pi, all those guys. They're neither infinitesimally small nor fantastically large. They're the numbers you meet in everyday measurements, calculations, the sort of comfortable middle ground.
Right, the ones we know and love. And then I'm guessing on the other end of the spectrum, the really enormous ones.
Exactly. Those are the unlimited numbers. These are just unimaginably huge. Numbers bigger than a Googleplex, numbers you'd need to measure distances across galaxies upon galaxies. And Just as we touched on, a really insightful property connects these extremes. If you take any non-zero infinitesimal, its multiplicative inverse 1 divided by it is always an unlimited number. And conversely, the multiplicative inverse of any unlimited number is always an infinitesimal. So there's this direct reciprocal relationship between the infinitely small and the infinitely large. It's a really powerful part of the hyperreal system.
So, okay, if the traditional real number line is like a piece of string stretched out, these hyperreals totally change its nature. They make it longer, right? With these unlimited numbers stretching out towards infinity at both ends. And at the same time, they make it way denser by adding all those infinitesimally close numbers, those halos around every single real number. It really is a hyperreal line.
You've nailed it. That's a perfect way to picture it. Now, you might be wondering, okay, new numbers. Do we have to relearn all of math?
Yeah, that thought definitely crossed my mind.
Well, the brilliant news is, not at all. The real beauty of hyperreal numbers comes with something called the extension and transfer principles.
Okay, extension and transfer. Those sound a bit hefty, academic maybe. What's the core idea, the practical takeaway for someone just starting calculus? What do they actually mean for us?
Right, they sound more complicated than they are in practice. The truly profound insight, really, is that these principles mean you don't need to rebuild mathematics from the ground up. They basically reassure us that all the fundamental arithmetic addition, subtraction, multiplication, division of Burney, and all the familiar rules for inequalities, the basic algebraic properties you learned for real numbers, they still hold true. They still work for hyperreal numbers.
Oh, okay.
So any theorem or statement that's true for real numbers and can be expressed in a particular formal way, well, it's also true for hyperreal numbers. It's incredibly elegant, actually.
Yep.
Very efficient. It lets mathematicians work with infinitesimals and unlimiteds directly, often making proofs and calculations much simpler.
So it's like moving from the familiar streets of your neighborhood, the real numbers, into a much bigger, more complex city, the hyperreals. But you don't have to relearn how to drive.
Yeah.
The traffic lights, the stop signs, the speed limits, they all work the same way. You just have way more streets to explore, more places to go. Is that a fair way to think about it?
That's a fantastic analogy, yes. It captures the essence perfectly. You're simply expanding your playground, not changing the fundamental rules of the game. And this lets us use all our existing algebraic intuition, our skills, to tackle problems involving these new kinds of numbers, which is incredibly empowering, really.
That's definitely reassuring. Okay, so we have these new types of numbers, infinitesimals, appreciable, unlimited, and the old rules still apply, thanks to extension and transfer. How do we best approach actually working with them then? Is there a smart way to learn the ropes without just getting totally overwhelmed by all the possibilities?
Absolutely. And this is where I think learning strategy comes in. To really master working with these new numbers, the material sort of implicitly encourages an approach that learning science backs up. Specifically, something Barbara Oakley talks about in A Mind for Numbers. Chunking.
Right.
Yeah. Instead of trying to just memorize every single possible outcome or rule, like infinitesimal times unlimited equals what, you group them into intuitive patterns, conceptual chunks.
Yeah.
This helps your brain build like mental frameworks rather than just storing isolated facts.
That makes perfect sense. It's about training your brain to see the bigger picture, right?
Yeah.
Recognize the patterns, understand why they work, not just what the rule is. Sounds way more effective than just rote memorization for gaining real insight.
Precisely. Think about these intuitive patterns for hyperreal operations. For instance, adding a tiny amount doesn't really change the size category. If you add an infinitesimal to an appreciable number, the result still appreciable. It's like adding a single speck of dust to a bowling ball. The bowling ball doesn't suddenly become galaxy-sized, you know? Or add two infinitesimals together. You just get another infinitesimal, maybe a slightly bigger speck of dust, but still just a speck.
Okay, that's one chunk.
Another chunk. Multiplying by something tiny tends to make things tiny, or at least smaller. If you multiply an appreciable number by an infinitesimal, the result is almost always infinitesimal, like hitting a normal object with a shrinking ray.
Got it. The shrinking ray chunk.
And a third one. Unlimited numbers tend to stay unlimited unless they're specifically canceled out. Multiply an unlimited number by another unlimited number. You get an even bigger unlimited number. They just keep growing, generally. These kinds of patterns help you make quick, intuitive judgments about the magnitude of your results without getting bogged down in every single case.
Those intuitive chunks seem incredibly helpful.
Yeah.
Huh? But what happens when the rules of thumb aren't so clear? Are there situations where these simple patterns kind of break down or don't give you an immediate answer?
Yes. And this is where it gets really interesting. This is where calculus, really earns its keep. Despite these generally clear patterns, there are definitely some mystery cases that demand a closer look. These are what we call indeterminate forms.
Indeterminate forms.
The source points these out clearly. Situations like dividing one infinitesimal by another, often written as aid, which kind of looks like 0, 0, or dividing one unlimited number by another hk, which looks like a. Or another common one, multiplying an unlimited number by an infinitesimal h, which looks like a times 0.
Right. So these are like mathematical puzzles where the answer isn't obvious straight away. You can't just apply one of those general chunks we just talked about. I think the book even shows examples where that product, h times a, could end up being infinitesimal or appreciable, or even unlimited. It depends entirely on the specific h and a involved.
Exactly. Think of these indeterminate forms like a tug of war. For something like hk, unlimited over unlimited, or h unlimited times infinitesimal, imagine two giant athletes pulling a rope. Both athletes are enormously strong, right? But who wins the tug of war? Well, it depends on the subtle details of their individual strengths, how much stronger one is than the other. Or for infinitesimal over infinitesimal, think about maybe two candles burning down. They're both nearly extinguished, getting smaller and smaller. If they're burning down at almost the same rate, which one is actually taller at some later point, it depends on tiny, tiny differences in their burn rates.
I see. So the outcome isn't predetermined just by the type of number involved.
Precisely. And the Kim insight here is that these indeterminate forms aren't dead ends. They're not errors. They are signals. They tell you, okay, pause. You need to do some more work here. Usually some algebraic manipulation or a deeper kind of analysis. For example, the source shows this. If you have a fraction like b squared minus 4b minus 21 divided by b squared minus 49, right? And you want to know what happens when b is infinitesimally close to 7? If you just plugged in 7, you'd get 0 over 0, indeterminate.
Right.
But if you factor the top and bottom first, you can cancel out the b7 term. Then you can see what the expression is infinitesimally close to. And that real number that the hyperreal expression is infinitesimally close to, that's often what we call the shadow or the standard part of the hyperreal number. That's the answer we're usually looking for.
Finding the shadow. I like that. Revealing the real number hidden inside the hyperreal expression. Okay, this definitely foreshadows a lot of what you end up doing with limits and derivatives in calculus, doesn't it? Figuring out these mystery cases seems like it's right at the heart of it all. So what does this all mean for someone who's just starting out, someone who might feel, understandably, a bit overwhelmed by these new ideas?
Yeah, it's completely normal for these ideas to sound strange, maybe even a bit mind-bending at first. I think the Calculus Unbound text even uses that phrase. Lots of students feel that way. And it's really not a sign of failure. It's actually a sign that your brain is actively stretching, building new connections. It's part of learning.
Absolutely. You definitely shouldn't worry about instantly getting everything or, keeping up with the intellectual racehorses, as Barbara Oakley puts it in her book. It's really a process. Think about learning to drive a car.
Good one.
At first, the steering wheel, the pedals, checking the mirrors, signaling, it all seems like totally separate, overwhelming things to manage all at once. But with practice, with patience, they start to feel natural together. You build the intuition, the muscle memory, and pretty soon you're navigating the roads with confidence, hardly even thinking about the individual actions.
Precisely. Confusion isn't a roadblock. It's actually a fundamental part of the path to getting insight. There's a great quote from Kenneth R. Leopold mentioned in the learning material. The learning process is all about working your way out of confusion. He says, articulating your question is 80% of the battle. So embrace that curiosity, ask the questions, allow your mind to wander and connect ideas, let your diffuse mode work its magic. And just remember that even the most challenging concepts eventually become clear with time and, some focused effort.
What a fascinating journey through the hyperreal line. So for everyone listening, you've discovered this powerful world of infinitesimals and unlimited numbers. You've understood how they expand our mathematical vision, like having both a microscope and a telescope for numbers. And crucially, you've learned that the old rules of math still apply. There's just vastly more room to explore now.
Exactly. And we've also highlighted the crucial role of chunking your learning, turning those complex operations into more intuitive patterns, and understanding that those indeterminate forms, they aren't roadblocks, they're actually invitations. Invitations for deeper algebraic exploration to find that essential shadow, that underlying real number value. Remember, that initial feeling of confusion, it's a powerful signal that real learning is just about to happen. Keep asking why, keep digging into the details, and you'll absolutely continue to uncover deeper insights.
So, for your next calculus adventure, remember to zoom in with that infinitesimal microscope and zoom out with your unlimited telescope. Keep practicing smart. Use those chunking techniques, and don't be afraid to embrace those mystery cases, those indeterminate forms. See them as opportunities to really master the material. What aspects of these infinitely small and infinitely large worlds will you explore next?